Okay, students, so let's start with the topic of electromagnetic induction and let's do some theory past papers for it. O levels in IGCSE physics. Let's start. So let's start with this question. Figure 7.1 shows a horizontal current carrying wire PQ in the gap between the poles of a permanent magnet. Okay, so this is a current carrying wire between the poles of a permanent magnet. Okay, there is a magnetic field between the gap between the north and the south pole. The current in the PQ is from left to right. Okay, so the current in PQ is from left to right. Okay, describe the effect of the magnetic field on PQ. Okay, so what will be the effect of magnetic field on PQ? The magnetic field on this current carrying wire will exert a force. And how can we calculate this force? By utilizing Fleming's left hand rule. Fleming's left hand rule always used to tell you the direction of force. The magnetic field is going up, so your first finger is up. Your current is going towards the right, so you will have your second finger like this, and your force will come out where? Your force will come out of the page. So you will say that the wire PQ experiences a force out of the page. Out of the page. Simple. Let's move on to part 2. State the effect on PQ of increasing the magnetic field in the gap. Okay. What will happen if we increase the magnetic field in the gap? It will experience a greater force. It will experience a greater force. Simple. Greater force out of the page. Out of the page. Let's move on to the next part. Figure 7.2 shows part of a torch. The torch does not contain a battery, okay? The torch is shaken and this causes the magnet to move backwards and forwards through the coil, okay? Explain why an EMF is induced across the coil when the magnet moves. Okay, why is an EMF induced across the coil when the magnet is moved? So as the magnet moves, what happens? Magnetic field lines cut with the coil. As the magnetic field lines cut with the coil, an EMF is induced. So you will say, as the magnet moves, as the magnet moves, magnetic field lines, magnetic field lines cut with the coil, cut with the coil. This causes an induced EMF. An induced EMF. State one way to increase induced EMF: use a stronger magnet. Use a stronger magnet. Okay. Let's move on to part 3. As the magnet moves into the coil, the induced EMF produces a current in the coil. Explain how this opposes the motion of the magnet. Okay. This is what? This is Lenz's law. Lenz's law used to state that the induced EMF flows in such a direction that it opposes the motion causing it. So, as EMF gets induced in this coil, as EMF gets induced in this coil, this develops its own magnetic field. So you will write this as your first point. As EMF is induced in the coil, it generates its own magnetic field, magnetic field. This magnetic field, this magnetic field opposes the motion of the magnet. This magnetic field opposes the motion of the magnet. Motion of the magnet. Okay. In simpler terms, as you can see, the magnet was pushed into the coil. So the magnet was applying a force into the coil that is towards the left. This coil will apply a force towards the right on the magnet. And how can this coil apply such a force? By inducing a north pole here. This will repel away the magnet. So this is what happens actually. Let's move on to the next one. Figure 6.1 is a view from the is view from above of a stationary magnet and a small compass on a laboratory bench. Okay. State the material from which the compass needle is made. Steel. Okay. Describe how the small compass is used to plot magnetic field lines in the region surrounding the magnet. Okay. How do we plot magnetic field lines region surrounding the magnet? So what do we do? Place the magnet, place the magnet, place the compass needle, sorry, place the compass near the magnet, near the magnet, near the magnet. Second point, mark a dot, mark a dot in the direction where the compass needle points, where the compass needle points, compass needle points. Okay. Let's say you have placed your compass somewhere here and your compass needle is pointing like this. So you will mark a dot where the compass needle points. Okay. What is your third point? Reposition, reposition the compass, reposition the compass such that, such that the backward end, the backward end of the needle, of the needle aligns with the dot, aligns with the dot, with the dot. So now we have to take the compass and reposition it at a new position where the backward end of the compass needle aligns with the dot, somewhere here. You can keep doing it. You can do it at multiple positions. Here, 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 here. You will get a complete magnetic field. Okay, then you can write the final point. Join all the points. Join all the points to get the complete magnetic field. Join all the points to get the complete magnetic field line. To get the complete magnetic field line. Magnetic field line. Let's move on to the next part. An unmagnetized iron bar, okay, an unmagnetized iron bar PQ is placed near to the magnet on the laboratory bench, okay. Figure 6.2 shows the two poles of the magnet and PQ, okay. So this is the permanent magnet, this is the iron bar. The iron bar is initially at rest and the magnet is moved towards the right very slowly, okay. So the magnet is moved towards the right very slowly. When the magnet is a short distance from the iron bar moves very quickly towards the left. Explain why the iron bar is attracted towards the magnet. Okay, so what will you say here? Why is the iron bar attracted towards the magnet? As the permanent magnet, as the permanent magnet moves towards the iron, moves towards the iron, moves towards the iron, the iron induces magnetism as it is a temporary magnet. What will be your next point? Your next point will be that the end P of the magnet and P of the iron bar becomes north. This becomes north pole. And P of the magnet and P of the iron bar, you will say, and P of the iron bar becomes north, becomes north. Unlike poles attract, unlike poles, attract, and iron bar gets attracted towards the permanent magnet, towards the permanent magnet. Simple as that. Let's further move ahead. Let's look at the next question. A computer disk contains a layer of magnetic material. Okay. Describe how a magnet is used to find out if a sample of material is magnetic or not. Okay. So place the magnet in front of or close to. Place the magnet, I would say close to. Place the magnet close to the magnetic and non magnetic materials. Magnetic and non magnetic materials. What will happen? Magnetic materials attract. Magnetic materials will attract the magnet. Magnetic materials attract the magnet. And non magnetic materials will not attract. Non magnetic materials will not attract. Simple. Let's further move ahead. Data is stored on a disk as a series of north and south poles. Figure 7.1 shows part of the hard disk. The thin layer of magnetic materials contain a small regions, okay? Each region has a north pole and a south pole. Some magnetic field lines are shown on figure 7.1, okay? Region 2 causes a magnetic force on region 1. Okay, this is region 1 and this is region 2. Region 2 causes a magnetic field on region 1. Okay. State the direction of magnetic force on region 1 and explain why it acts. Okay, what will be the direction of magnetic force on region 1? Towards the left. Because these are like poles. Can you see? This is not, this is not. They are like poles. Like poles repel. Okay, so yeah, you can say towards the left. Towards the left. Why? Because like poles repel. Simple. Let's further move ahead. On figure 7.1, draw arrows on the field lines to show the direction of the magnetic field near the boundary between region 1 and 2. Okay, so you have to show the direction of the field line. You will say north to south, north to south, north to south, north to south. And here the arrows will emit away from north. Okay, let's erase this arrow. This is getting confusing. Yeah, so these will be your magnetic field lines. The coil shown in figure 7.1 is in fixed position. The layer of magnetic material pass quickly under the coil. Okay, so this is the coil. The layer of magnetic material pass under the coil. Okay. A voltage is induced in the coil as sum of the boundary between the region pass under the coil. Okay. Explain why a voltage is induced. Why is a voltage induced? Very easy to answer. The magnetic field. Magnetic field. Magnetic field lines. Magnetic field lines cut with the coil. This induces EMF. Suggest why the coil must be close to the layer to generate a higher voltage. To generate a higher voltage. I would say not use generate, but instead use the word of induce to induce a higher voltage. This is an examination keyword. Let's move ahead. Figure 8.1 shows a step down transformer used to operate an electric bell. Okay, state the material used for the core of transformer, soft iron. A current in the primary coil produces a magnetic field in the core. Okay, explain how an alternating voltage is produced in the secondary coil. Very, very easy. Very easy. The current or the alternating current in the primary coil, in the primary coil generates generates changing magnetic field. Generates changing magnetic field. Second point, these field lines cut with the solenoid, cut with the solenoid, or you can say secondary coil, cut with the secondary coil. This cutting effect or this change in cutting effect does what? This change in cutting effect produces an alternating voltage in the secondary coil. Produces an alternating voltage in the secondary coil. An alternating voltage in secondary coil. In secondary coil. Let's further move ahead. Okay, let's see this. The transformer has 4600 turns on the primary coil. This becomes what? NP, which is connected to a main supply of 230 volts. This becomes your voltage primary. And output voltage of 5 volts is used to operate the bell. This is your voltage secondary. Calculate the number of turns on the secondary coil. We have to calculate NS. So Vp over Vs is equals to Np over Ns. What is the primary voltage? 230. What is the secondary voltage? 5. What is the primary number of turns? 4500. What is the secondary number of turns? Ns. Can you calculate the number of turns on the secondary coil? Yes, 230 divided by 5 and 4500 divided by answer. The number of turns comes out to be 98. 98 or 97. Yeah. State one change that can be made to the transformer shown in figure 8.1 so that it can be used as a step up transformer. Reverse the coils. Reverse the coils. Make the secondary coil as the primary coil and the primary coil as the secondary coil. Let's see this. Figure 6.1 shows part of a toy which contains two ring shaped permanent magnets. A plastic rod passes through the center of both magnets. Okay. The top magnet can move up and down freely around the plastic rod. The magnetic poles on the bottom magnet are shown in figure 6.1. The top magnet floats in air above the bottom magnet. On figure 6.1, mark the poles of the top magnet and explain why it floats in the air above the bottom magnet. Okay, when can the top magnet float above the bottom magnet? If both of them have like poles facing each other. So I have marked the poles, and secondly I can write like poles repel. I mark the poles on the top magnet and explain why it floats. Like pole repels, hence it floats above the bottom magnet. Above the bottom magnet. Let's further move ahead. Let's move on to the next part. The top magnet is placed with a ring made of iron. Okay. Explain why the iron ring sticks to the bottom magnet. Okay. Now we have replaced the top magnet with what? We have replaced this top magnet with an iron ring. Okay. Why does the iron ring sticks to the bottom magnet? Why? Because iron is a temporary magnet. Is a temporary magnet, and it induces poles opposite to that of the bottom magnet. To that of the bottom magnet. And if iron induces poles that are opposite to that of bottom magnet, what will happen? Unlike poles attract, unlike poles attract, and iron sticks to the bottom magnet. Iron sticks to the bottom magnet. Simple as that. Let's further move ahead. A current carrying wire. A wire carrying a current passes at right angles through the piece of paper. Okay. Figure 6.2 shows a cross and a circle where the current in the wire passes into the plane of the paper. Okay. On figure 6.2, sketch three magnetic field lines to show how the magnetic field line pattern around the wire. Show the direction of field line on your sketch. Okay. So this is a wire that is carrying current into the plane. If you are carrying current into the plane, which type of magnetic field lines form around the wire? Clockwise direction. Let's make it. And there is one more thing that you need to be really careful about. There is one more thing that you need to take care of. 1 second. Yes, somewhat like this. Let's mark the direction as well. So, in the clockwise direction, the second thing that you need to take care of is the distance between consecutive field lines should increase. The distance between consecutive field lines should increase. Somewhat like this. Yeah. Let's make the last line because in marking schemes, usually you have to make 3 lines. So the distance between consecutive field lines should increase and all of the field lines will be in the clockwise direction. Like this. Let's further move ahead. Figure 9.1 shows a permanent magnet lying on a piece of paper. Okay. Underline the material in the list from which it is possible to make a strong permanent magnet. It is possible to make a strong permanent magnet from steel. Okay. Describe an experiment to plot the pattern. We have already done this. We have already done this in a previous question. Let's further move ahead. Figure 9.2 shows the north pole of a magnet placed in front of a south pole of a second magnet. Okay. A section of a horizontal metal wire JK lies in the magnetic field between the two magnetic poles. Okay. End K of a metal wire is connected to a positive terminal of a battery and end J is connected to the negative terminal of the battery. Explain in terms of electron why there is a current in the wire and state the direction of the conventional current. Why is there a current in the wire? Due to the flow of electrons, and electrons carry charge, and electrons carry charge. Simple. What is the direction of conventional current? The conventional current always flows from positive terminals to negative terminals. Conventional current always flows from positive terminal to the negative terminal, that is from point J to point K. Also, I am just thinking about this line. Explain in terms of electrons. Here you can also write that electrons electrons get repelled get repelled from from terminal J from terminal J, that is the negative terminal, and get attracted towards terminal K, that is positive, towards terminal K. You can also add this as a key point, towards terminal K, that is positive. The part of JK in a magnetic field experiences a force. State the direction of force and state how this direction was reduced. Okay. So your direction of flow of current is this from from positive to negative. Okay. You have to calculate the direction of force. You will apply Fleming's left hand rule. Left hand rule. Magnetic field is flowing into the page like this. Current is going like this. Let's apply Fleming's left hand rule. Magnetic field into the page. Current like this. Force will act downward. The force will act downwards like this. Okay. So what do we have to state in the question? This is a 4 marker question, so it will require some working. First of all, you have to state the direction of force F. The force F acts downwards. The force F acts downwards. Okay, so the force F acts downwards, and how was this direction reduced? By applying Fleming's left hand rule. Applying Fleming's left hand rule. What does Fleming's left hand rule states? Index finger in the direction of magnetic field. Direction of magnetic field. Second finger where? Second finger in the direction of current. Direction of current. Where does the thumb points? The thumb points in the direction of force. Simple as that. Let's further move ahead. The equipment in figure 9.2 is used in a similar experiment. Okay. The part JK that lies between the poles of a magnet now passes through a long iron tube. Okay. That's a problem. Why? Because iron will absorb all of the magnetic field lines and no magnetic field lines will pass over the wire. The tube is shown in figure 9.3. JK is connected to the battery in the same way as before. State what happens to the force on the wire. The force on the wire will become zero because all the magnetic field lines are shielded by this iron tube. Force becomes zero as all the magnetic field lines, as all the magnetic field lines, magnetic field lines are shielded, are shielded by the iron tube. Shielded by the iron tube. Simple. Let's further move ahead. Iron tube and the wire JK are removed. Okay. A square vertical coil is placed between the poles so that the plane of the coil lies in the magnetic field as shown in figure 9.4. Okay. Explain why the coil tries to rotate when there is a current in the coil. Why does the coil starts to rotate when there is a current in the coil? So the top side, the top half, or you can say the top side of the coil experiences a force, and the bottom side experiences a force in the opposite direction. So you can say the top surface of the coil of the coil experiences a force in one direction, a force in one direction, and the bottom surface experiences a force in the opposite direction, and the bottom surface experiences a force in the opposite direction. In the opposite direction, this causes the coil to rotate. This causes or this results, this causes in a moment, this causes a moment which rotates the coil, which rotates the coil, which rotates the coil. Simple as that, nothing complicated. Let's further move ahead. Let's see this. Figure 9.1 shows a simple relay used to switch a mains electric motor on and off. Okay. So this is a simple relay used to switch on and off an electric motor. Okay. Uh, Explain why the motor switches on when switch S is closed. Okay. So as switch S is closed, what happens? As you close switch S, what happens? The core gets magnetized. The core gets magnetized. And as the core gets magnetized, what will happen? As the core gets magnetized, what will happen? This core will attract the iron armature. The core attracts the iron armature. Okay. As the core attracts the iron armature, what will happen? The top side, or the you can say, yeah, the top part of the armature forces the contact to close. The top part of the iron armature of the iron armature forces the contact to close, forces the contact to close. Okay. Explain why the coil, yeah, core is made of iron rather than steel. Okay. Why is this coil or core. Why is this core? Sorry. Why is this core made of iron and not steel? Because steel is a permanent magnet. And what are the harms of a permanent magnet? Steel is a permanent magnet. Hence, 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 even after, hence, after opening the switch, hence, hence, after, hence, even after opening the switch, hence, even if the switch is open, even if the switch S is open, the core will remain magnetized. The core will remain magnetized. The core, let me correct it. The core will remain magnetized, will remain magnetized, and the motor will still be on, will still be on, still be on. Let's move on to part 3. Our student suggests that the motor can be turned on and off without a relay. He suggests connecting the main supply to a simple switch in series with the motor. Okay. So he suggests that remove the relay. Okay. Suggests why in some situations using the relay is better. We can operate a high voltage circuit with a low voltage switch. We can operate a high. We can operate. We can operate a high voltage circuit using a low voltage switch. Simple as that. Let's further move ahead. Let's see this. Okay. Figure 9.2 shows Figure 9.2 shows the coil of a wire wrapped around a cardboard tube. There is no core. Okay, there is no core. There is an electric current in the wire in the direction shown by the arrows. Okay. On figure 9.2, draw the pattern of the magnetic field lines around the coil. Mark the direction of this magnetic field. Okay. So if I apply right hand grip rule here, 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 my fingers curl in the direction of the current. Where will my thumb point? My thumb will point towards the right hand side. You can do it yourself as well. If your thumb points, basically, if your fingers curl in the direction of the current, like this, your thumb will point in the direction of the north. This is north, this will be south. Now, how will the magnetic field lines be plotted here? Once I have stated that right hand side is north, left hand side is south, how will I plot the magnetic field lines? Very, very easy. Okay. So magnetic field lines emit from the south and they go inside the south. They emit from the north and they go inside the south like this. So you mark the direction as well like this, and you have to make sure that you make the field lines inside the solenoid as well. Like this. Emitting from the north and going into the south. Let's make two more lines here. Like this. Should I remove this right hand grip rule? Yeah, let's remove this right hand grip rule. Something along these lines. Let's make an other field line as well. Here. Starting from here. Okay. Starting from here. And curling back like this. This is from where your magnetic field lines emit. They go into the south like this. Okay. And one more field line you can draw that is emitting. Let me keep north here. That is emitting from the north like this. One is going straight like this. One is curling like this. You can extend them backward as well, like this. This is going into the south. Yep. This is like this. And yeah, these are your field lines. However, after second thought, I think I shouldn't have drawn this one. Let's erase this. This will make the field lines more tidy. Yep. Not always drawing something extra is useful. I have seen the marking scheme as well. It also suggests you to just draw one line on both sides going from north to south, and then three lines you can draw like this. Yeah, this looks more tidy. Let's further move ahead. On figure 9.2, mark the North Pole. We have already done that. The supply of the current of the coil is removed. Okay. The ends of the coil are connected to a sensitive ammeter as shown in figure 9.3. Describe how a permanent magnet is used to produce a large reading on the ammeter. The permanent magnet, the permanent magnet is permanent magnet slash steel is pushed backwards, or I would say is moved backwards and forwards, is moved backwards and forwards inside or in front of the coil, in front of the coil at a faster rate. Why faster rate? Because you need to generate a large reading on the ammeter. So what will you say? The permanent magnet steel is moved backward and forward in front of the coil at a faster rate. This will generate your voltage. Okay. Explain why a current is produced in A. Very easy. The magnetic field lines, the magnetic field lines, the magnetic field lines, field lines cut with the coil, with the coil. This change in cutting effect, this change in cutting effect induces current, induces current. Let's further move ahead. The metals in the list below have different uses. Okay. State which metal from the list is used for a compass needle. Steel. State which metal is used for magnetic screening. Iron. State which metal is used for the core of a transformer. Iron. Describe one use of a transformer. It is used in power transmission, power transmission or electricity transmission from the power plant, from the power plant to households, to households. And what is the function of transformer in this power transmission or electricity transmission? It changes the magnitude of voltage. It changes the magnitude of voltage. Simple as that. Let's further move ahead. An AC generator supplies an input voltage of 220 volts to a transformer. In the space below, sketch a graph for the output voltage against time for an AC generator. I guess we have done this, but I think we did this in the current electricity thing. So yeah, let's draw your voltage versus current graph. It will look something like this. It will look something like this. Somewhat like this. Also make sure to label the axis. Y axis will be your voltage, voltage output in volts. X axis will be time in seconds. Okay. Now let's further move ahead. The transformer has 1700 turns on the primary coil and 85 turns on the secondary coil. Determine the output voltage. Very easy. What was your input voltage? 220. So NP over NS is equals to VP over Vs. What is NP? 1700. What is NS? 85. What is VP? Number of voltage in the primary coil? 220. Can you calculate the secondary voltage? Yes. 1700 divided by 85. Okay. And 220 divided by answer. This gives you 11 volts as your secondary voltage. Let's further move ahead. Figure 11.1 shows a magnet next to one end of a solenoid. Okay. The terminals of the solenoid are connected to a very sensitive ammeter. The magnet is moved towards the right like this. Okay. At a constant speed, and a reading is observed on the ammeter. Okay. Explain why there is a current in the ammeter. We have discussed this so many times. Magnetic field lines cut with the solenoid. The change in cutting effect induces EMF. This EMF generates current. This current is read by the ammeter. So you can write it by yourself. This is very, very easy now. Explain how the current in the ammeter opposes the change causing it. This is a good question. This is also repeating, but this is a good question. This is Lenz's law. The current in the coil causes the solenoid to become a magnet. This current, you can first of all write this. The current in the coil induces magnetism inside the solenoid. Okay. What will happen as your second point? The magnet is pushed inward. The magnet is pushed inwards. It is moved towards the right. How can the solenoid oppose it? By pushing it towards the left. This is the left force that the solenoid will apply. How can the solenoid apply a leftward force? By inducing a south pole here, north pole here. So what will you write? The solenoid pushes the magnet away by inducing a south pole on the left side. And since like pole repels, there is a force towards the left hand side. Let me reread the answer. The current in the coil induces magnetism inside the solenoid. Okay, the solenoid pushes the magnet away by inducing a south pole on the left. Simple as that. Now let's read this. The magnet stops when the south pole reaches the middle of the solenoid. Okay. The reading on the ammeter is observed. Okay. When the magnet is moved towards the left at a constant speed that is less than the speed in C1. Okay. Now you are pulling the magnet away but at a lesser speed. Okay. State two ways in which the reading on the ammeter will be different. First of all, it will be in the opposite direction since you are pulling the magnet now. And secondly, it will have a lesser magnitude. Why? Because you are pulling it with a lesser speed. Let's further move ahead. Figure 9.1 shows a simple AC generator. Explain why there is a voltage induced in the coil when the coil is turned. Very, very easy again. As the coil is turned, what happens? The magnetic field lines. I think I have written this answer for the fourth time in this entire video. Magnetic field lines cut with the coil. This change in cutting effect induces a voltage. Simple as that. In figure 9.1, the coil is horizontal with side AB on the left. Okay, side AB is on the left here. Okay. The output voltage is 6 volts. Okay. On figure 9.2, draw a line from each of the shaded boxes to one of the circled voltages to show the output voltage when the coil is in different positions. Okay. One line has been drawn for you. When the coil AB is on the left, you have 6 volts. When the coil AB is on the right, your voltage flips. You get a negative value of 6 volts. And when the coil AB is on the top, your voltage is 0. When the coil AB is on the bottom, your voltage is 0. Simple as that, you have drawn all the arrows. Both AC and a DC motor contain a coil and brushes. Figure 9.1 shows how the brushes are connected to the coil of an AC generator. Okay. Draw a diagram to show how the brushes are connected to a coil in DC motor. Okay. So brushes are connected somewhat like this. First of all, you need to remember that in a DC motor, you have split ring commutators. Let's label it as well. These are split ring commu commutators. These are split ring commutators, both of them. And these are your carbon brushes. Let's also label the carbon brushes somewhat like this. These are your carbon brushes. Okay. How is a coil connected to it? The coil is connected somewhat like this. Oh, I think I will have to minimize this. Slightly to draw a coil. Let's draw a coil now. Somewhat like this. A coil is connected. Yep. Like this and like this. This is your coil. This is how a coil is connected with carbon brushes in a DC motor. Let's label this as a coil as well. State why there are forces on the side of a DC motor. Okay, why are there forces on the side of a DC motor? Very easy again. Very easy again. The current carrying coil cuts the magnetic field, generating a force, generating or inducing a force, generating a force. Let's further move ahead. Okay, let's see this. An electric circuit consists of a battery, a variable resistor, and connecting wires. Section P, Q, and QR of the connecting wires are in a region of space where there is a uniform magnetic field. Okay, there is a uniform magnetic field, and you have wires P, Q, and QR. Okay, in figure 7.1, shade the shaded area represents the magnetic field. Okay, so this one was shaded area. This thing is the shaded area, and this represents magnetic field going into the page. As you can see here, the important part is what? Magnetic field going into the page. The direction of the magnetic field is into the page. A current carrying wire in a magnetic field can experience a force. Okay. In the table, mark one tick in each column to indicate the force on PQ and the force on QR. Okay. So always remember, current flows from positive to negative. So in PQ, your current will be like this. Your magnetic field is into the page. Your current is like this. Where is your force pointing? Where is your force pointing? Your force will point towards the top of the page like this. A force towards the top of the page. This is your answer. For QR also, your current will flow downward. Okay. So your magnetic field is into the page. Your current is downward like this. 1 second. Your current is downward like this. This is your second finger. Your current is downward like this. Where will your force point? Towards the right. Towards the right like this. This is your force. Uh, do we have any option like that? Yes. Right. The battery in 7.1 is reversed. Okay. State and explain the effect on PQ and QR. Both the forces. Since the current reverses, see what will happen if the battery reverses. The current reverses, and since the current reverses, the forces will also reverse on both PQ and QR. You can say since the current reverses, the forces on PQ and QR both reverse. Simple. Let's further move ahead. The variable resistor is adjusted and the current in the circuit decreases. Okay, suggest one effect of decreasing the current. The force decreases. Simple. Let's further move ahead. Figure 7.1 shows a metal rod placed between the poles of a magnet. Okay, this is a metal rod placed between the poles of a magnet. This is a positive terminal, negative terminal. Current always flows from positive to negative. Okay. End A of a rod is connected to the positive terminal of a DC power supply, and end B is connected to the negative terminal. Yeah, that's visible. The current in the rod and the magnetic field produce a force on the coil. Okay. On figure 7.1, draw an arrow to show the direction of the current in the metal rod. You have to show the direction of the current and label it C. So the direction of current is this. Okay. The direction of the magnetic field that acts on the metal rod, label this arrow M. Okay, so the magnetic field will be like this. This is your arrow M. Okay. If your magnetic field is flowing like this, current is like this, where will your force act? Can you calculate the force? Yes or no? Can you calculate the force? Very easy. Now let's move on to the third part. The direction of the force on the rod, label this F. Okay, so how will you calculate the direction of force? Magnetic field is outward, current is inward, the direction of force comes out to be downward like this. We have to label this F. So something like this. This is your force F. Let's further move ahead. The power supply is removed and a sensitive voltmeter is connected between the ends A and B. When the wire is moved upwards and downward, there is a reading on the voltmeter. Explain why there is a reading on the voltmeter. Again, same answer. As the coil moves up and down, the coil cuts with the magnetic field. The change in cutting effect produces an EMF. That EMF is recorded on the voltmeter. The reading on the voltmeter is increased by using a stronger magnetic field. Okay, state one way of producing a larger reading on the voltmeter. Use more number of turns on the coil. Use more number of turns on the coil. Simple. Let's further move ahead. 1 second. Let's make this correct. Two flexible iron strips WX and YZ are placed close to each other inside a solenoid long coil. The end W of WX and the end Z of YZ are held firmly in position. Okay. The switch is closed. Okay, the switch is closed. What happens? And there is an electric current in the solenoid. And W of a flexible iron strip WX becomes a south pole. So this becomes your south pole. What will X become? X will become North Pole. If X is North Pole, what will Y become? South Pole. If Y is South Pole, will Z become? Z will become North Pole. So we have to write everything here. Z is North Pole, Y is South Pole, X is North Pole as well. State and explain what happens to X and Y because the flexible iron strips are magnetized. As flexible iron strips get magnetized, they attract towards each other and close the circuit. Simple. A relay operates a switch in one circuit using the current in a different circuit. State one example of a relay used in this way and explain why a relay is used. Maybe in nuclear power stations or general power stations. Why is a relay used here? To switch on a high voltage device using a low voltage switch. Using a low voltage switch. Simple. Let's further move ahead. Figure 5.1 shows a simple DC motor used in a toy car. Okay, what are points? This and this. This is a carbon brush. And what is this? This is a split ring commutator. Simple. Okay, on figure 9.1 add labels, we have done that. Okay, the number, state what happens to the rotation of the coil when the number of turns on the coil is increased. the rotation speed increases, or you can say the force increases, speed of rotation, or you can say force increases. The the magnetic field between the poles of the magnet is reversed. The direction of rotation reverses. Direction of rotation reverses. Simple as that. Let's further move ahead. The power supply for the motor is switched on and off at a steady rate. Figure 5.2 shows how the speed of the toy car varies with the time as a result of the power supply being switched on and off. Describe the motion of the toy car. Okay. As the power supply is switched on, is switched on. This causes what? This causes the speed to increase, increase and reach a maximum value. This causes the speed to increase and reach a maximum value. And reach a maximum value. However, when the power supply is switched off, when the power supply is switched off, what happens? When the power supply is switched off, the speed decreases and reduces to a minimum value. Reduces to a minimum value. Okay, let's further move ahead. The voltage supplied to the motor is switched on for a longer period of time and off for a longer period of time at a steady rate, suggests what happens to the motion of the car. The terminal speed, or you can say the motor, what happens? The voltage supplied to the motor is switched on for explain what happens to the motion of the toy car. Okay, the toy car maintains a constant speed for a longer duration of time. Maintains a constant speed for a longer duration of time. Longer duration of time. And when it is switched off for a longer period of time, what will that do? When the power supply is switched off for a longer period of time, what will that do? And the toy car reaches a lesser or a lower minimum velocity, reaches a lower minimum minimum velocity or speed when switch is off. When switch is off. Simple. Let's further move ahead. State whether coil A or coil B in the transformer has the larger number of turns. Give a reason for your answer. Okay. So this transformer is connected close to the house. Close to the house, you have step down transformers. In step down transformers, the primary coil has more number of turns. Coil A has more turns. Why? Because it is a step down transformer. Step down transformer. And in step down transformers, what happens? Number of turns on the primary coil is greater than the number of turns on the secondary coil. One purpose of using an iron core in the transformer is to increase the magnetic field inside coil A. Okay. State one other purpose of using the iron core to increase the cutting effect in coil B. Increase the cutting effect in coil B. Simple. Briefly describe how an output voltage is induced in coil B. This is the working of a transformer. We have already done this. Let me tell you what you have to write here. You will say that the alternating voltage in coil A generates a magnetic field. This magnetic field cuts with coil B. As magnetic field cuts with coil B, this This generates EMF. Simple. State one advantage and one disadvantage of burying a power line underground rather than having an overhead power line. Okay, what are the advantages? It saves the power line from storms and rain. What is a disadvantage? It is expensive to do that. Expensive to do that. Let's further move ahead. A loudspeaker is made from a coil of wire fixed to a cardboard tube. The tube is attached to a cardboard cone. Okay. Figure 8.1 shows part of the arrangement of the loudspeaker. Okay. When there is a current in the coil experiences a force. State what else is needed in the loudspeaker to make a current carrying wire experience a force. Magnetic field or magnets, you can say that. Magnetic field or magnets. A student connects the coil of the output of an alternating current generator. Show how the electromotive force produced by the generator varies with time. Okay, so this is the induced EMF versus time. Okay, the coil tube and cone vibrate forwards and backwards. Explain why EMF shown in figure 8.2 makes the coil vibrate. Okay, so the EMF is what? Sometimes in positive, sometimes in negative direction. This causes the coil to move forwards and backwards, causes it to vibrate. The direction of EMF keeps on changing, keeps on changing. This causes this causes the direction of force to change continuously, continuously. Hence the coil vibrates. Hence the coil vibrates. Let's further move ahead. The vibrating coil produces sound in the surrounding air. Explain in terms how the coil produces a sound wave that travels through the air. So you will say the vibrating cone produces or causes, or the vibrating cone causes the air molecules to vibrate. Okay. As the air molecules vibrate, as the air molecules vibrate, they generate they generate compressions that are regions of maximum pressure and rarefactions that are region of minimum pressure. As the air molecule vibrate, they generate compression and rarefactions. Last point, this causes the transfer of sound or transfer of energy, and sound waves are developed. Sound waves are generated. Sound waves are generated. Simple as that. Let's further move ahead. Sound is a longitudinal wave. State the difference between a longitudinal and a transfer wave. In a longitudinal wave, the direction of disturbance is parallel to the direction. In a longitudinal wave, the direction of disturbance is parallel to the direction of wave travel. And in a transfer wave, what happens? The direction of disturbance is perpendicular to the direction in which wave travels. So it's pretty easy. I think I have done such a question in waves theoretical papers as well. Use figure 8.2 to determine the number of times that the cone reverses its direction of motion in 1 second. Okay. So from the graph, can you calculate the time period? Yes. Time period is 0.05 seconds. Can you calculate the frequency? Yes, you can surely calculate the frequency. You can surely calculate the frequency as well. Okay, so if you visualize here, what was the time period? 0.05 seconds. Okay, can you calculate the frequency here? Yes. Frequency is equals to 1 over time period. 1 over 0.005. 1 divided by 0.005. Your frequency comes out to be 200 hertz. But please don't write this as your answer. Because can you see In one wave, the direction is first of all in the positive, then it becomes negative. So if one wave is completed, that means your coil or cone has changed the direction two times. So if the frequency is 200, that means the direction change is what? 200 into 2, that is 400 times. There comes your answer. The speed of sound is this. Calculate the wavelength of sound. Okay, very easy. So V is equals to F lambda and okay. We are given the frequency. We are given the speed. We can do that. 340 is equals to 200 lambda. 340 divided by 200, the lambda comes out to be 1.7. 1.7 meter is your lambda or wavelength. Okay, let's see this. Figure 9.1 shows a cathode ray oscilloscope. An alternating voltage supply is applied to the input and the trace produced is shown. Okay. The Y gain is set at 5. The time base supply is set at 2. Okay. Use figure 9.1 to determine the maximum voltage of the supply. Okay, you have to determine the maximum voltage of the supply. First of all, you will determine the mean position. This is your mean position. The maximum point is two boxes. The maximum point is two boxes away from the mean position. And one box on the y-axis represent 5 volts. So two boxes will represent what? 2 into 5, that is 10 volts. This is your maximum voltage. Describe how the trace on the screen and the controls on the CRO are used to measure the time between 2 points on the trace. Okay. How can we calculate the time between 2 points on a trace using the CRO controls and this trace? First of all, first of all, count the number of boxes between 2 points on the trace. Then what will you do? Multiply this number with what? Multiply this number with the time base setting. Multiply this number of boxes with what? With the time base setting or with the time base supply. With the time base supply. Simple as that. Let's further move ahead. Okay, so this is the end of electromagnetic induction past papers. If you have any questions, you may ask.